Imagine that for one impossible moment, you could remove everything from reality. No stars, no planets, no atoms, no light, no space, no time, no quantum fields, nothing. Now ask the question that may be more disturbing than any question about black holes or the beginning of the universe. Why is there anything left to remove? We usually ask where the universe came from, but that question quietly assumes something already exists. It assumes there is a universe, a physical reality, perhaps a set of laws, and then asks what happened before all of it. But Leonard Susskind's way of thinking about fundamental physics forces us toward a deeper problem. Before asking how the universe evolved, we may have to ask why there is a universe to evolve at all. And this is where the mystery becomes almost impossible to escape, because physics has become extraordinarily good at explaining how things happen once reality exists. We can describe the birth of stars, the collapse of galaxies, the behavior of particles, the expansion of spacetime, and the violent interior of black holes. Quantum mechanics tells us how microscopic systems behave. General relativity tells us how gravity shapes spacetime. Cosmology tells us how the universe developed from an extremely hot, dense early state into the enormous structure we see today. But none of these explanations automatically answers the most primitive question. Why these laws? Why this universe? Why something rather than nothing? For centuries, questions like these were mostly the territory of philosophy and theology. Physics could describe the motion of planets, but it had little to say about existence itself. Then, during the 20th century, something extraordinary happened. The universe stopped looking like a collection of objects sitting inside an empty stage. Space and time became physical. Gravity became geometry. Matter became deeply connected to fields. And at the quantum level, even what we call empty space turned out to be far stranger than ordinary intuition suggests. The vacuum is not simply a perfectly featureless nothing. In quantum field theory, what we call empty space is associated with quantum fields that permeate the universe. Particles can be understood as excitations of these fields. The electron is not merely a tiny ball flying through an otherwise empty void. It is associated with an electron field. Photons arise from the electromagnetic field. Other particles emerge from their corresponding quantum fields. So when physicists say empty space, they do not necessarily mean absolute nothingness, and that distinction is crucial. Because imagine someone claiming that quantum mechanics explains why the universe exists. They might say that the universe could emerge from a quantum vacuum, but immediately another question appears. Where did the quantum vacuum come from? Where did the quantum fields come from? Where did the laws governing them come from? And why should there be quantum mechanics in the first place? We have not escaped the mystery. We have simply moved it one level deeper. This is one reason the question, why does anything exist, is so difficult. Every explanation seems to depend on something else already being there. The universe expanded because of certain physical conditions. Those conditions followed certain laws. Those laws operate on a particular mathematical structure. And suddenly we find ourselves asking whether physics can ever explain the existence of the framework within which physics itself operates. Leonard Susskind has spent much of his career working at precisely the frontier where these questions become unavoidable. His work on black holes, quantum mechanics, string theory, and the holographic principle has repeatedly challenged the simple idea that reality is exactly what it appears to be. Perhaps the most famous example is the black hole. At first, a black hole seems like an object that should simplify our understanding of existence. It is just a region of space-time where gravity becomes so intense that nothing can escape once it passes the event horizon. But black holes created one of the deepest crises in modern physics. According to general relativity, information that falls into a black hole appears to become inaccessible. According to quantum mechanics, information should not simply disappear. That conflict became known as the black hole information paradox, and Susskind became one of the central figures in the argument that nature must preserve quantum information. Why does that matter for the question of existence? Because information may be far more fundamental to reality than we once imagined. The holographic principle, developed through work by Susskind and others, suggests that the amount of information contained in a region of space may be related not to its volume, as ordinary intuition would suggest, but to the area of its boundary. Think about that. You could imagine a three-dimensional room containing objects, particles, and fields. Yet the fundamental information describing everything inside might somehow be encoded on a two-dimensional surface surrounding it. This is not the claim that our universe is literally a movie projected onto a cosmic screen. That popular description is much too simplistic. The deeper idea is that the number of fundamental degrees of freedom in a gravitational system appears to be constrained by area, and that possibility changes the way we think about what reality is. If space-time itself can emerge from deeper quantum information, then space may not be the foundation. It may be a consequence, and if space is emergent, perhaps time is not as fundamental as it seems either. That leads to an unsettling possibility. Maybe the universe is not fundamentally made of things sitting inside space. Maybe what we experience as space, time, matter, and even geometry are different manifestations of something deeper. But again, the question survives. Why does that deeper structure exist? Physics has a remarkable habit of answering one question by creating an even more profound one. Newton explained planetary motion, and humanity discovered universal gravity. Einstein explained gravity through space-time, and humanity discovered that space and time themselves could bend. Quantum mechanics explained microscopic behavior, and suddenly observation, probability, and information became fundamental parts of physical theory. Modern cosmology describes an evolving universe, and we are forced to confront the extraordinary fact that the laws of physics appear capable of producing complexity, structure, stars, chemistry, and eventually observers who can ask why any of it exists. But perhaps the strangest clue comes from the universe's earliest moments. The observable universe was once dramatically hotter and denser than it is today. As the universe expanded, it cooled. Eventually, particles formed atoms. Gravity gathered matter into stars and galaxies. Stars forged heavier elements. Planets formed around later generations of stars. Everything we see has a history, but how far backward can that history go? The standard cosmological picture leads us toward an extremely early universe where our familiar description of spacetime eventually becomes inadequate. General relativity works extraordinarily well under enormous ranges of conditions, but it is not expected to be the final theory when quantum effects and gravity become equally important. That is the regime where a theory of quantum gravity is needed, and this is where the mystery of existence becomes connected to one of the greatest unsolved problems in physics. We do not yet possess a universally accepted theory that completely unifies quantum mechanics with gravity. String theory is one major candidate framework. In string theory, the fundamental entities are not point-like particles, but tiny extended objects whose different vibrational modes can correspond to different particles. Susskind was one of the early pioneers of string theory, but string theory produced another surprise. Instead of giving us one obviously unique universe, it appears to permit an enormous landscape of possible vacuum states and physical configurations. Different solutions can correspond to different low-energy physics, different particles, different forces, different constants, potentially different forms of physics. And now another terrifying question appears. If many physically possible universes or vacuum states exist, why are we in this particular one? One proposed answer is the anthropic principle. Perhaps we observe a universe compatible with life simply because observers can only exist in universes compatible with observers. That statement is logically straightforward, but it is deeply controversial when used as a fundamental explanation. It may tell us why our observations have certain properties without telling us why the underlying theory has the structure that permits those possibilities in the first place. And this is where scientific humility matters. There is currently no established experimental evidence showing that our universe was selected from a proven multiverse by some cosmic mechanism. The multiverse remains an active and speculative idea in several areas of theoretical physics and cosmology. So we should not confuse an interesting possibility with an established fact. But the possibility itself reveals something important. Maybe the laws of nature are not uniquely determined in the way we once hoped. Maybe physics does not have to produce one inevitable universe. Maybe reality can support many possibilities, and our universe is one particular realization. If so, existence becomes less like solving a single equation and more like understanding a vast space of possibilities. But there is another path. Perhaps there is no deeper explanation. Perhaps reality simply exists. That sounds almost trivial, but it may be the hardest possibility of all. We are psychologically conditioned to expect causes. Every event we encounter seems to have an explanation. A glass breaks because it falls. A star forms because gravity collapses matter. A galaxy evolves because physical processes operate over billions of years. So when we encounter the universe itself, our instinct is to ask what caused it. But what if causality is itself a feature of the universe? What if what happened before the universe is not a meaningful question because time itself is part of the physical system being described? Consider the surface of Earth. If you stand at the North Pole and ask, what is north of the North Pole? The question sounds reasonable grammatically, but geographically it breaks down. North is defined as a direction on Earth's surface, and beyond the North Pole, the concept changes. The same kind of problem may occur with time. If time began with the universe, asking what happened before the universe might be like asking what is north of the North Pole. This does not prove that time began with the Big Bang. The exact nature of the earliest universe remains an open problem, but it illustrates why ordinary language can fail when we push physical concepts beyond the domain where they were developed. And perhaps existence itself is like that. Maybe asking why reality exists assumes a framework of explanation that only makes sense inside reality. That would mean the universe does not need a cause in the ordinary sense. But that answer still feels unsatisfying. Because even if time begins with the universe, we can still ask why the underlying physical laws exist. And then we reach a boundary where physics begins to overlap with philosophy. Susskind has often emphasized the lesson that runs through modern theoretical physics. Nature does not owe us an intuitive explanation. The universe is under no obligation to match human common sense. Quantum mechanics already demonstrated this. A particle can exist in a superposition of possible states. Entangled systems can exhibit correlations that cannot be explained using simple classical pictures. The quantum state does not behave like an ordinary object carrying definite classical properties at every moment. General relativity demonstrated something equally radical. Time does not flow identically for everyone. Clocks can tick at different rates depending on motion and gravitational conditions. Space is not a rigid container. It can curve. It can expand. It can evolve. And black holes reveal that space, time, quantum theory, and information cannot be treated as completely separate concepts. So perhaps the biggest mistake is assuming that reality must resemble the mental picture our brains evolved to construct. Our brains were designed, in an evolutionary sense, to navigate forests, recognize faces, avoid predators, find food, and cooperate with other humans. They were not designed to intuit quantum gravity. Yet somehow, using mathematics, experiments, telescopes, particle accelerators, and sheer imagination, humans have managed to discover structures of reality that no human being could directly experience. That is perhaps the most extraordinary fact of all. The universe can be understood by creatures that occupy an almost unimaginably tiny corner of it. And the deeper we investigate, the stranger the relationship between observer and universe becomes. If the fundamental description of reality is quantum mechanical, then what exactly is an observer? Does consciousness matter? Does observation physically create reality? Popular culture often takes quantum mechanics and leaps toward these conclusions. But established physics does not require human consciousness to magically create the universe. Quantum measurement is a technical physical process, and physicists can describe it without invoking mystical consciousness. Yet quantum theory still leaves profound interpretational questions. What exactly constitutes a measurement? What is the correct interpretation of the quantum state? Is the wave function a physical object, information about a system, or something else? Different interpretations answer these questions differently. And again, we should separate what we know from what we imagine. The equations work, the experiments work, the deeper meaning remains debated. Now consider something even more unsettling. What if existence does not have a single level? Perhaps asking why the universe exists is like asking why a particular sentence exists in a book. You can explain the sentence using the paragraph using the chapter using the book using the author, but eventually you reach the boundary of the explanatory chain. At some point, something has to be taken as given. Physics may simply move that boundary farther than any previous science. We once took Newton's laws as fundamental. Then came deeper principles. We once treated atoms as indivisible. Then discovered nuclei and electrons, then quarks, then quantum fields. Perhaps what we call particles are not fundamental either. Perhaps space-time is not fundamental. Perhaps information is deeper. Perhaps even the mathematical structures we use to describe physics are shadows of something more fundamental that we have not yet discovered. And perhaps there is no final layer at all. Maybe reality is an endless hierarchy of explanations. But if every explanation requires another explanation, then the chain never reaches a foundation. That possibility is almost as strange as a universe appearing from nothing. And this brings us back to the word nothing. Absolute nothingness is difficult to define. If there are laws, it is not nothing. If there is space, it is not nothing. If there is time, it is not nothing. If there is a quantum vacuum, it is not nothing. If there are mathematical possibilities, is that nothing? We often use the word casually, but absolute nothingness may not even be a physical state. Physics describes states of physical systems. Nothing may not be a state at all. Perhaps this is why the question, why is there something rather than nothing, remains so resistant to scientific explanation. We are trying to compare reality with an alternative that may not correspond to any physically meaningful possibility. And yet the question continues to haunt us because existence feels contingent. We can imagine a world without Earth. We can imagine a universe without stars. We can imagine different particles. We can imagine different constants. We can imagine no human beings. But can we genuinely imagine absolute nothing? No space to imagine it in. No time in which it exists. No laws governing it. No observer thinking about it. The moment we try to picture nothing, we usually create an empty space. But empty space is already something. Maybe existence is not an accident, sitting on top of nothing. Maybe nothing is not the default. Maybe existence is the default, and what we call nothing is the abstraction. That possibility turns the original question upside down. Instead of asking, why does something exist? Perhaps we should ask, why did we ever expect nothing to exist? We do not know. And science does not currently provide a final answer. But this uncertainty is not a failure, it is the frontier. The deepest questions are often the ones that expose the limits of our current theories. Susskind's work reminds us that reality may be encoded in ways radically different from our everyday experience. Black holes force us to confront information. Holography challenges our assumptions about dimensions. String theory explores the possibility that particles and forces emerge from deeper structures. Quantum mechanics challenges classical certainty. Cosmology confronts us with the origin and evolution of the universe itself. Taken together, these ideas do not give us a simple answer to why anything exists. They do something more interesting. They show us that the question is probably deeper than we first imagined. Maybe existence is not about objects. Maybe it is about relationships. Maybe it is about information. Maybe space-time itself emerges from quantum degrees of freedom. Maybe our universe is one realization among many possible physical structures. Maybe there is a deeper theory waiting beyond quantum mechanics and general relativity. Or maybe the final explanation will not look like an explanation at all. Perhaps, at the deepest level, the universe simply is. And if that is true, then the strangest thing is not that we have failed to discover why reality exists. The strangest thing is that reality exists at all, and that within it, a small collection of atoms became organized enough to look outward, build mathematics, discover black holes, question the nature of information, and eventually ask the universe why it is here. Every star above us is part of the same physical story. Every atom in your body was shaped by cosmic history. Every thought you have is produced by matter following laws that existed long before there was anyone around to wonder what those laws meant. And now, after billions of years of cosmic evolution, the universe has produced something capable of asking a question that may have no answer inside the universe itself. Why is there anything? Perhaps that question is the beginning of our understanding, or perhaps it is the boundary beyond which understanding itself changes meaning. And maybe the ultimate mystery is not why the universe exists, but why there is a universe capable of asking why it exists.